Hello everybody, we are here doing lesson 3, solubility equilibrium. So I've been sort of hinting at this the whole time that this is really another unit on equilibrium. And what we talked about last time was how there are certain combinations of ions which are unnaturally, or naturally I guess in this case, solid in solution. These combinations of ions tend not to dissociate because they have very strong ionic bonds, and they have very weak ion dipole interactions. So these are compounds with strong ionic bonds, and or weak ion dipole interactions. In fact, any chemical will have this type of equilibrium where they form a solid. Any ionic compound does have this kind of solubility equilibrium, but it will depend on concentration before it becomes relevant. So chemists will indicate this equilibrium using this type of chemical symbol notation. We almost always will put the solute on the left, and discuss it as the reaction from the solute forming the two dissolved species. Now, once again, I'm going to remind you that if it is aqueous, then it has a concentration, and therefore, if it has a concentration, then we have a situation where there will be an effect from increasing or decreasing those concentrations in terms of shifting the solubility to the left or the right. So since no more solute molecules can be dissolved at saturation, as water molecules collide with the solid solute particles, the solute dissolves. However, as a solute particle dissolves, a dissolved solute particle leaves solution and becomes solid again. This occurs simultaneously. So what they're saying is that at an equilibrium point, this will be the point where the solution has the maximum amount, the maximum concentration for these two ions. So solvation of these different salts is only possible up to a certain concentration of these ions because of this equilibrium existing. So saturated solutions is a chemical solution that contains the maximum concentration of solute dissolved in the solvent. Additional solute will not dissolve in a saturated solution. So maybe I should go through some definitions here. Solute is the solid part, the solid that is being dissolved. So this is a solid that was added to a solvent, and this solvent is usually water. Okay, perhaps that should be written out as text. So that's what a solute is. A solvent, usually waters are solvents, especially in this situation. It is simply the liquid that you are dissolving your solute in. So the solubility product. This is substances chemists believe that to be insoluble in water by experiment were shown to be slightly soluble. That is, with very sensitive instruments, chemists were able to show that substances that would not dissolve in water actually do dissolve to a very small extent. When a sparingly soluble ionic solid is dissolved in water to form a saturated solution, the general equilibrium equation is this. So here's where the number of those ions in the solid molecular equation are represented by these subscripts, and those become the coefficients in the chemical reaction as the solution, as the compound falls apart, the ionic compound falls apart into two composite ions. So this is where A is the positively charged ion and B is the negatively charged ion. And so if this is an equilibrium, then for any given temperature, the equilibrium law will be K equals the concentration of that A ion raised to the power of A times the concentration of that B ion raised to the power of that coefficient B divided by the concentration of this AABB, except that this is a solid, right? So this is a solid, so that means no concentration. Or actually, a better way of writing this is actually an infinite concentration. The concentration is not changing, or maybe therefore, that's probably the best way to say it, is an unchanging concentration. So here KQ is called the new constant, and that constant is going to be called KSP as we remove this solid piece. And so that gives us the new equilibrium law. KSP is equal to the product of the two composite ions and their concentrations. The solubility product constant, KSP, is the product of the ion concentrations in a saturated solution. So here is a type of question we might have to write. Write the dissociation equation and the expression for the solubility product constant for a given example. So write this for calcium hydroxide. So calcium is a 2+ ion. Hydroxide is an OH1-. So that means together, these form calcium hydroxide. We need two of them because the charges need to be equal. This is a solid. And so that will dissociate into calcium 2+, and then it will be aqueous. And we'll be adding hydroxide ions, two of them, because there's a 2 here, and those will also be aqueous. And so although earlier we talked about in the terms of solubility rules, calcium hydroxide is considered insoluble, there will always be a very, very tiny amount of that calcium hydroxide that still sneaks its way into solution. And that we'll be able to determine exactly how much of that is in solution by finding the KSP or looking up the KSP and then using this ion concentration calculation. Remember that it's going to be raised to 2 because of that coefficient on that hydroxide. All right, so here's another one. This is a lead phosphate. So they've already given us the chemical. So I'm going to just write out the rule here. This is the solid. This is that same lead compound that I was talking about. It's one of the options you can use when you have lead in your pipes. So this KSP will be very, very small. And there's going to be 2 of those. So then for the KSP expression, we need to write lead 2+ and raise it to the power of 3 for that coefficient, multiplied by PO4 3- raised to the power of 2 for that coefficient. And there we go. So that's how you write a solubility product constant expression for that chemical reaction. So now if you have this type of expression, then you should be able to calculate the KSP if you know how many ions there are in a saturated solution. So if at equilibrium, and when they say at equilibrium, they are meaning a saturated solution. So that's at a saturated solution. The concentration of silver ions is 1.3 times 10 to the -5 molar, and that's my silver ion concentration. And the concentration of chloride ions is 1.3 times 10 to the negative 5. Wow, what a small amount of chlorine, right? Then what is the KSP? Well, silver chloride will be like this. It's a solid, so I would expect you to be able to write out your expression here. And this is really just the flipped version of the net ionic equation we talked about last time. And we'll come back to that later. That's a little hint. So then we're going to punch in, we're going to create a KSP expression first so that we have something to punch in. And then we're going to punch those equations in. 1.3 times 10 to the negative 5. We're multiplying that by 1.3 times 10 to the negative 5. You could use you could do 1.3 squared if you wanted. I'm going to pull up my calculator here, and I'm going to show you that. I'll show you some trickery here. If you are familiar with the exponent rule, then we can actually estimate that this is times 10 to the negative 10 because we're multiplying two exponents that have the same base, and by base I mean they have both a 10 in the base. It's 10 to the power of negative 5. So when you multiply things of the same base, then you can just add their exponents. So that gives us 10 to the negative 10, and then I just have to do on my calculator, and I could even do this on a very simple like regular one-line calculator or a 6-function calculator. 1.3 times 1.3, and that's 1.69. So I'm actually done. So that's the equation. It is technically mole squared, but as we've done in the past, KSPs don't really have units. Okay, so there's a practice question. I'll fill that out and upload that later. So I'll let you practice that at home. You might as well pause at this point if you want to continue. And then I'm going to go on to the next example. Okay, so the next type of question is going to be one where we calculate solubility using KSP. So solubility and KSP are tightly connected to each other. The solubility is the chemical property referring to the ability for a solute to dissolve in a solvent at a certain temperature. The solubility product constant is an equilibrium constant and has only one value for a given solid at a particular temperature. So the solubility product constant, that would be the KSP, right? This KSP is an equilibrium constant that has only one value at a given temperature. So if you know the KSP, you will know the equilibrium concentrations of the component ions of that chemical, and that therefore tells you the solubility of that chemical. So the solubility of lead fluoride is 0.466 grams per liter. What is the value of the solubility product constant? Okay, so this can be really tricky. There's a lot of stuff going to go on right here. So first things first, I need to think about that I have lead fluoride, and this is going to be this is a solid, and it's dissociating to form lead and lead 2+, aqueous, and fluorine, 2 fluorines, also aqueous. Now, this reaction is actually able to happen. This here, which is going to be the equivalent of writing a lead fluoride aqueous. And we actually know the concentration of this value from this solubility that they've given us. So, but there's some problems here. One problem is that solubility in this format is often used in industry where they don't care about moles. They care about something they can measure. And what they can measure in a industrial setting is weight. They can say, hey, hand me that 1 kilo bag of lead fluoride and I will add it to this 1 liter of water that I can also measure with a volumetric flask or whatever. So they are often dealing in the values of mass, not in the values of molarity. So something we haven't done in a very long time, I imagine, for many of you, is we need to be able to convert grams per liter into moles per liter. So to get to the from grams per liter to moles per liter, we are going to multiply by a value of moles per gram. And this is, of course, molar mass ratio. So that's a grade 11 skill coming back to hopefully not haunt you, but we'll see. So I'm going to take that 0.466 grams per 1 liter, and I'm going to multiply that by a ratio of 1 mole of this chemical. So this chemical is lead, which I believe is 207. I'm actually going to open up another window here that's you guys can't see, but you can trust me. Lead has a mass of 207.2 grams for 1 mole, plus the value of fluorine, which is pretty much 19. 19 to the number of decimals we need. So there are 2 of them, so 2 times 19.0, and that's also in grams. So I'm going to take that. I'm going to also find my calculator here, and I'll put that over here. So let's combine those first. 27.2 plus 2 times 19, and we get a value of 0 times 1 mole divided by 245.2 grams. So I'm going to take that 0.466. I'm going to multiply that by 1 divided by 0.2. Even better on a calculator that does fractions nicely. And the value I get is, I'm going to do it in scientific notation, 1.90 times 10 to the negative 3. And that's the molarity. Now, watch out, because that's the molarity of this thing, right? But notice that this thing has a 1 to 2 ratio for the fluorine. So we also need a KSP expression, which is equal to the concentration of lead times the concentration of fluorine squared. And so I'm going to have, I know what the concentration of lead is at solubility. I know the concentration of lead is 1.90 times 10 to the negative 3 molar, but my concentration of fluorine is actually going to be a 1 to 2 ratio, so I actually get twice as much. So I'm going to get almost 4, so 3.8 times 10 to the negative 3 molar. Cut off a 0 there. Okay, so I'm going to take that and I'm going to run with it. I'm going to find my KSP by punching in that equation. 1.90 times 10 to the negative 3 times 3.80 times 10 to the negative 3 squared. And the result will be 1.9 e negative 3 times 3.8 e negative 3, and raise that to the power of 2. So the KSP is surprisingly possible, maybe surprisingly, 2.7 times 10 to the negative 8. I think at one point I probably only had 2 significant figures there, or 1 decimal place. All right, yeah, right around here. So that is my final value. That's how you find a KSP. It's a bit of work, but you can do it, and I believe in you. Okay, so for the next question, we're going to be calculating the ion concentration from the KSP. So this is almost the reverse of the previous question. So here we have a KSP value, and we want to know what is the equilibrium concentration of the dissolved ions in a saturated solution of this magnesium hydroxide. So again, always valuable to write out your equation first. So here's your solid. It's going to be dissociating a little tiny bit into aqueous magnesium plus 2 hydroxide ions. Okay, so then we have a KSP equation. Okay, and it says, what will be the equilibrium concentration of the dissolved ions in a saturated solution? So this can be a relatively challenging question. So I'm going to keep this to the side, as I'm going to go back to an old favorite, the ICE table. So what is the equilibrium concentrations? It's a very simple ICE table. For these two equations, as some of this, right? It doesn't have a concentration, so we don't care about it. But some of this is going to be converting to these ions. So we're going to be thinking about this as this side of the equation is increasing by x and increasing by 2x on this side. And that leaves us with x and 2x as our concentrations. So what would happen to this equation over here if we replace these values with these x values? So this is what we would be left with. Your math skills can be put to work here. You're going to get 4x squared, and that means that your total is 4x to the power of 3. So I combine the x and the 2x, or the x squared, to get x3. And then my KSP, which I was given, is 8.9 times 10 to the negative 12. So let's see what happens when we take the cube root and divide by 4. So we're going to divide by 4 and then take the cube root of 8.9 times 10 to the negative 12. So I'm going to get my calculator out. I'm going to set up a cube root, 8.9 e to the negative 12, and I'm going to also divide that by 4, and I'm left with a value of 0.1. Oh, well, I should write it in scientific notation, right? 1.3 times 10 to the negative 4 is equal to x. When in the case of doing a cube root, it's worth noting that taking a cube root of an exponent means to simply divide the exponent by that root. So in this case, negative 12 divided by 3 would actually leave you with negative 4. So that would be a good estimate if before even applying this, the 4 as well that we also have to apply. And of course, you should use a calculator, but in the case where you had to do this at home or whatever, or away from a calculator, that would be our value. So what will be the equilibrium concentrations of the dissolved ions? We're almost there. We have to punch these in. We have a 1.3 times 10 to the negative 4 molar for the first ion, and the other ion will be 2.6 times 10 to the negative 4 because we have twice as much hydroxide as we do magnesium. And this could be important because in our next unit we're going to talk about pH, and pH is highly affected by the amount of hydroxide. So maybe dissolving a little bit of magnesium hydroxide into a solution, you might end up causing your solution to gain a change in pH. All right, what is the solubility in grams per liter for magnesium hydroxide when the KSP is 8.9 times 10 to the negative 12? So let's say we completed all of this previous example. We have, you know what, I'm going to cheat. Look at this. Here's how I'm going to do this. So this is all the steps you would have to do. This all still applies. So I'm going to just copy that. I'm going to paste that here. And then all you're going to do in this version of the question is you're going to use the ratio, right, of magnesium hydroxide to magnesium. Notice that it is 1:1 for the magnesium to magnesium hydroxide. So the concentration of Mg2 plus is equal to the concentration of magnesium hydroxide, in this case, that is aqueous. Right? So in this case, we know that the magnesium hydroxide, so magnesium hydroxide, aqueous, has a concentration equal to 1.3 times 10 to the negative 4 molar. Okay, but that's in moles per liter. So we have 1.3 times 10 to the negative 4 moles per 1 liter. And now we're going to times that by something in terms of grams divided by 1 mole. And that would be our molar mass. And to do that molar mass, I'm going to have to put in the molar mass of magnesium, which is 24.3. So 24.3, that's magnesium in terms of grams, plus 2 oxygens, so that's 2 times 16.0 grams, plus 2 times 1.01, and that's plus 1 plus 2 times 1.01 grams for the hydrogen. And the result here is 1.3 E negative 4 times, and please do put a bracket around this because otherwise you will only be multiplying by the first number. 2 times 16 plus 2 times 1.01. Close that bracket, and the result is 7.5 times 10 to the negative 3, and that, let's make it, round that up there, 6 times negative 3 grams per liter. And so that is how you can convert from moles to grams. And this is a much more useful number, not as easy to get to, but it is more useful for practical sense. All right, you have some practice questions there. Please try to do some of those. We'll be doing some of those during the classroom meetings as practice, and you'll see those videos possibly in the future if we get a chance to record them. All right, and have a great day.